computed. Okay, hello everyone. Thanks again for joining us today, another Friday. I think today is going to be an interesting class. So as always, thanks. And please, if you have any question, just ask it. As I said in the mail, I think it may be better if you just ask the question instead of using the chat, because I cannot really read and talk. So feel free to just raise your hand or just ask a question. I think it's very important because we can learn some things, and sometimes I say something that it was not the same thing I was thinking that I wanted to say. So if you can correct me or just ask the question, I think it's better. And also, as I said, if you ask the question, then it will be recorded. So people that see the recordings later, they can also learn a bit more about your question and the answer. So please don't feel afraid. Just stop me and then we can chat. Okay. So then I will start sharing the presentation. Today is day 4. As I said in the mail yesterday, we are going to continue with the atoms configuration, atoms of input, and related files to this file. And in particular, we are going to learn how to solve the non-Lte problem. That this is something that we did last week, but now also considering partial redistribution. We will study the impact on 3 transitions from the same atom. So we know that the calcium 2 atom that we are using can produce 5 transitions, the 2 blue transitions H and K, and then the 3 in the infrared. So we are going to study 2 cases, a case where PRD is almost negligible, and a case where PRD is really important. And then the aim is to really allow you to decide first how to do it, how to add or not PRD, and also to allow you to study for a different transition that you may be interested on, how to compute or estimate when you need to use PRD and when it's almost okay to not doing it. Okay, so then let's move to the script. As always, we are inside RH, RHF1D, and so this is the 1D distribution. And I'm creating a new folder, that this is the one I will share with you later. So we will be here, okay? So then let's start with the script. I think you can see it well. If not, just let me know. So as I said, we are going to consider partial redistribution today, and we will focus on 3 transitions, the calcium 2 H and K, and the 8542, the infrared transition. So let's start with the atoms.input file. So if we go here, it's the same configuration we have last week. So we have several atoms, and then we have that only one is inactive. That is the one that we want to compute accurately the populations of the level and the transitions between those levels. Okay, so then with that, we move to the calcium atom. Here we have that, as we are going to also check in detail the calcium H and K transitions, I decided to add more points. So we have 100 and 100. We said that it was better, even if we were focusing on the infrared transition, to also set as asymmetric the H and K. So we leave it like that, but it comes from last week. And then the rest of the atom, it remains the same. Okay. So then just as a comment, and I think Han will add maybe a bit more on that. Usually I just work on PRD with intensity. In principle, the code allows you to do it with polarimetry, but it may not be the best depending on what you are interested on. So well, I will just allow him to just explain what I mean.
Yeah, so in principle, the code will work with PID and polarimetry. Well, for one, the code only takes into account the Zeeman effect. So PID is important when scattering is important, and so also in that case, probably scattering polarization is probably more important. So we don't take into account all effects. So how well you reproduce the physics doing that is not very easy to define or to figure out. So I would be hesitant a little bit to use to do polarimetry inversions with PID, like in the calcium H and K lines. Now, typically when you do though polarimetry in 8542, you probably should still do PID in the H and K lines, because it does influence the populations, and therefore because the H and K lines share the same upper level as the 8542 and the other triplet lines, it is important for the populations of those upper levels to treat calcium in PID in the H and K lines, even if you don't use the signal in the lines themselves for the inversion. So I would say still use PID, but take if you would want to invert H and K with PID and polarimetry, I would be very careful in interpreting things.
Mm-hmm. Okay, thank you. So then for today's example, we will just keep everything on intensity. So we will not take into account the magnetic field, and we will not compute the Stokes profile. So then what we do is that we go to the keyword.input, and you go down to the last part, that is where we configure the magnetic field, and you put it like this. That is what I have here as a note. So you just comment the line where you are providing the file with the magnetic field information, and then in the Stokes mode, you just set no Stokes. Okay, so then the code will just focus on intensity. Okay, so then with this, we can just run the code. So we'll do it like this. And then as last week, we have that the code converges to a solution. So if you remember, we said that it was okay to provide a relatively large number of iterations and then a relatively demand.
No.
I think, yeah, sorry, I muted. so then in this case, we are reaching the convergence, and this is, we are now in the same case as last week, so CRD. So we are just doing non-LT iterations, and then we reach convergence at, in the 16th iteration, okay? So this is what I'm saving in this file. Now, I'm not doing it now, but it's the one that you will see in the folder. And this is what I'm calling CRD, okay? So I'm just reading, I'm saving the wavelength information, the intensity for the projection in mu equal 1, so this center. And then later you will see, but now we don't need to worry about this, but I'm also saving two ideal structures that are called spectrum and geometry. You will see why I do this later, but important is wavelength and intensity is what I'm saying. Okay, so then now we'll go to the second case, that is where we want to add PID. Okay, so we need to do several things. The first one is we go to the atom. So inside the atom, so then RH will allow you to specify PID for a specific transition. Okay, so then you remember that this void meant CRD, so you need to just change void by PID in the transition of interest that you want to solve in PID. The rest of the rest of the transition will be solved in CRD. So then, as we said, let's solve calcium 2 H and K, and also 8542. Okay. So then with this, we are going to ask the code to solve PID for these three transitions, and these two will be in CRD. Okay. I added here a note. So before compiling, I will just go through the note, and it's something that is related with what Hans said before. So my advice is that when you are starting to use an atom and you want to check the impact of PRD on a given transition, probably the best thing is to switch PRD for all the transitions. So imagine in this case, we set PRD for all the transitions. And then you run the code. And after that, then you start removing PRD from the transitions that are not you are not interested on them, and check every time that you remove transitions if there's no impact on the transition of interest. And this is because some transitions may also be related with the level that is involved in the transition of interest that you are looking for. And then adding PRD for those transitions solves better the population as well. And then it can improve the accuracy of your level. So I added a bit of self-advertising here. This is a publication, and I added in the Dropbox folder. And here you can see that in our case, when we were solving Lyman lines, in particular Lyman beta, we did this exercise. We set PRD for all the Lyman transitions and check if they had an impact on Lyman beta. And we realized that Lyman alpha, that is the dominant transition, it has a strong impact on Lyman beta. So in order to properly solve Lyman beta in PRD and with accuracy, you also need to solve Lyman alpha and PRD. So then, as an exercise, you can add this one, also the one that Hans proposed, but I think this one could be interesting. So try to reproduce after this class what happens if you solve, for example, if you are focusing on calcium H and K, if you put this line as like this, void. So if you have a lower accuracy or a different result when doing it like this or like this. So in other words, as those lines, they populate the ground level. So maybe in order to properly solve this one in PRD, you also need to solve this one in PRD. So this is something that you need to investigate and to try a bit. But what Han was saying is, in fact, as these lines, they have the upper level, that is the 4. And this one, the calcium 8542 also has the same level. So it may be necessary to solve those lines in PRD to obtain the best accuracy on the populations, to have better accuracy on calcium 8542. So just imagine levels, and with PRD, you are populating those levels with better accuracy. And as those levels will populate a different transition, that is the one that you're interested on, so then you need to add PRD on calcium H and K. But this is something that you can play with. So if you switch on and off PRD and you don't see changes, so then maybe it's not necessary. So just try to play a bit and try to understand what is happening. Okay. So in this case, I think it doesn't matter because we are just checking what is happening. So we are going to switch on only PRD, calcium H and K, and then 8542. Okay. So then if we have, then we need to go to the keyword.input. And this was the instructions for the non-LT problem. And then just after that, you have the instruction for the PRD computation. Okay. And then you have something similar as before. So you have a number of maximum iterations and a number of, or the limit that you want to achieve. So what I add here is that if this is commented like this, if you put PRD in the calcium atom, the code will run with PRD, okay? This is by default. If you uncomment this line and you put here 0, this is what I'm writing here, then it will be CRD, okay? So the result of this computation should be exactly the same as the previous one, even if we add in PRD on the atom. But if you add a number here, for example, I think this is advisable. So like 10 iterations and then 1 10 to the -3 or 10 to to the -3. Then if you run, you will see that now there's a lot of text here. And, and now we will check it. So later, so you can see that now you have some information here, and then you have additional things here, okay? But before going there, just let's check the rest of the parameters. So here we have ng acceleration, and we saw this last week, and we concluded that in the case of the non-LT computation, in most of the cases it was working, but in some cases it was working, it was worse. So then it's something that you need to check. So for this test, I will just focus on solving the PID, and I will not add the ng acceleration. Later we will see a bit more about that. And then finally, there's this last sentence that is also here. And it's saying, if you want, there's two ways of computing PRD inside RH. One is the angle average PRD computation, and the second one is the angle dependent. So in general, the default computation is angle average, but if you are interested, you could add angle dependent. That in principle is more accurate, but it's really time consuming. So in general, and for today's example, we are only going to use the angle average, but it's something that you may want to look at. Okay, and finally, this XRD, I say something about it here. So there are some different contributions to the scattering that you take into account in PRD. And this cross redistribution, it's aiming to take into account the Raman scattering. So it's just an additional layer of complexity, but accuracy at the same time. So today I just use it as default, and I think it's false, but you may also want to try what happens if you put true. Probably the results will be a bit more accurate, but you should check it and check if the time difference is worth it of the accuracy you gain. Okay, so today is very simple. Angle average, and we are not including cross redistribution. And I think I had a note here. So before taking into account the results, yes. So what I was saying is that for this study, we just do the computation from last week where we had 5 rays. Remember that we were saying that RH is solving the radiative transfer equation for different heliocentric angles, and this depends on the number of rays that you have here. So then what we are doing is solving the 5 rays and then calling solve ray for computing the radiative transfer or the profile at heliocentric angle equal 1. But if I'm correct, Han, I think this is not applicable on the angle dependent PID, right?
Angle dependent, you cannot use the solve ray. Right. No.
Okay. Okay, so then just take a note of this. So if, yeah. Okay, I thought there was a question. So just today's example is angle average. That is probably the most standard that you can use. And we can follow the same procedure as last week. So using solve ray to computing the profile at a given heliocentric angle. But if you are using angle dependent, don't use solve ray, because in principle it will not work. If you want to know a bit more how you can compute a specific angle with angle dependent, I can give you as an advice to play a bit with the number of rays. We will see later what 5 rays means. And then from there, you will have an idea of if you're interested on some heliocentric angle, you may add more rays until you cover that heliocentric angle. But for today's, we are going to keep it as simple as possible. So in the keyword.input, we specify a number of iterations and a reasonable limit. We don't use ng. and we are using angle average, that is default, and we don't include cross redistribution. Okay. So then I run the code as I did, and I'm going to save the file. We will use this later, but let's start to check what is in the screen. So we have that the code reached a convergence in iteration 12. Let's see what was happening before. So you have this iteration. It's a non-LT problem that we had last week. This is the relation between the radiative transfer equation and the statistical equilibrium equation. And then we enter on this, just 1 second, yes. And we enter in this PRD now cycle. You can see that PRD iteration, and then there's also a delta value, okay? So then we solve the populations, we enter in the radiative transfer equation, and now we start iterating PRD. And this is for a given solution of the statistical equilibrium equations. We iterate until we reach the accuracy that we are asking, and then we run a new computation of the statistical equilibrium equation, and it's this one. Okay, so now imagine that we have a big loop that is statistical equilibrium equations and radiative transfer. So this was the last week loop, and now we have an extra loop in the radiative transfer part where we add in PRD. So then this is the numbers that you're seeing here. This is the bigger one, and this is the inner one that is new now, okay? And also you can see that there's 3 entrants per iteration. And this is the 3 calcium lines, so line 0, 1, and 4. If you go to here, you will see that they are here. So this line 0, 1, and 4, okay? So then, and yes, and every loop of the PRD, you are obtaining the merging spectrum, and then the code is checking. So in this case was 9 to the minus 3. So then it tries to iterate again, and then now it's 6 times the minus 4. That is lower than the limit that we ask. So then we finish here, we solve the statistical equilibrium equations, we enter again in the loop, we reach the convergence for the 3 transitions that we are solving in PRD, and then we run again on LT. So in this case, we are already in the bigger loop in the limit that we are asking the code, and then we are also here in the limit that we are asking the PRD part, okay? So these are the 2 different numbers that we see here, okay? So then we can conclude that the computation was properly done. Both the non-LT problem and the PRD computation was complete. So then I'm saving now this as a lambda 2 and Stokes I2, okay? So I think this is all I said here. Yes, and I'm saying also that FALC, it's very easy to do. We will check bifrost later if we have time. But in this case, I tried NG acceleration, and it's a bit slower. So again, you may try things. If you see that your configuration with a given atom and atmosphere, it's having a benefit from NG acceleration, then use it. And if not, you can just leave it out and use it only in the non-LT problem, okay? Because you can see that the non-LT part is already accelerated. What we are not accelerating now is the PRD computation, okay? So then this is what we had. So now let's do some plots, because I've been talking a lot and showing you a lot of numbers, and maybe you are a bit lost. So then just let's try to visualize what we are doing, okay? So then, as always, you will have a folder with high definition figures. So then let's start with calcium 8542, okay? So then I will make it bigger. Okay, so in this case, we have run at the beginning of the class the problem in CRD. So we solved the non-LT problem, but in CRD for all the transitions. And this is the blue line, okay? And then we added, sorry, this is the orange line. And then we added in the atom PRD for the calcium 8542 transition, and then we solve the non-LT plus PRD problem, okay? And now we overplot them, and you can see that there's a slight difference between the blue and the orange one, okay? So you can see that it's a bit higher in the core, but we also see some difference here. But in general, we can say that it's relatively small. And the reason is that if we do the same for calcium H, you can see that there's also a small difference between the PRD and CRD computation in the core, but then there's a much larger difference in the inner wings, okay? And then we have the same for calcium K, okay? So the difference here is small, and then here is much larger. So then now we can see that for mu equal 1, you can already see difference between CAD and PRD. They are relatively small for a calcium infrared line and much larger for the calcium H and K. Okay, but we can take a step further, and we can say, okay, PRD in general, I think I have already covered this. Yes. So then what happens if instead of looking at this center, we have also different heliocentric angles? So then it means that we have a different geometry and projection effects. And I think there is where you can really see much more impact of PRD. Okay, so then we are going to do several steps that are useful for today's example, but also I hope it will be useful for you for future checking of other things. So then what we're going to do is first, we read the structure's geometry and spectrum. So if you remember, I said at the beginning, I'm saving, just one second. I'm saving the structure geometry, geometry and spectrum. So when you use the read all function that I put it here, when you use this, it reads everything. So you will have, for each computation, you will have spectrum, geometry, Atmos, and a lot of things. Okay, so now we are going to use first geometry and then spectrum. Okay, so then if we go up to this point, if we do this, okay, I don't know, I think, yes, let me, so if I do help geometry, okay, you have a lot of things. And if you do print geometry.xmu, okay, you have 5 values. And those values are the heliocentric angles at which, so where RH solves the radiative transfer equation, okay? So then we can, in fact, check the intensity profile for different heliocentric angles. We are using solve ray for computing mu equal 1, but the code already for solving the non-LT problem is computing also the intensity for 5 different heliocentric angles. Okay, so where are those 5 intensity profiles? So they are in a spectrum. Okay, so if you type help spectrum, there's also a lot of things, and we have here I. Okay, so if you type help spectrum.I, you will see that it's an array of 371 times 5. So these 5 are the 5 rays that are computing at these 5 heliocentric angles. And then 371, if you see lambda is also 371. So this is the intensity profile, okay? So then essentially it means that we can already compute or plot the difference between PRD and CRD for those 5 heliocentric angles, okay? So let's try to do that. So I will show you the figure, and then if you want, we can cover how I did it, or just you can watch it later. It's not so difficult, but there are some lines here. But let's go to the figure first, okay? So if we go to 8542, there's a lot of things, so just let me go slowly. So in the upper part, we have intensity profile, okay, just in the central part of the line. Then we have colors, 5 colors. So those colors are the heliocentric angles that RH used to solve the radiative transfer equation. I put it in a simplified way. They are exactly, you can see it here, it's not exactly 0, it's not exactly 0.25, this is 0.50, this is close to 0.75, and this is not exactly 1, but just for the plotting, I think it's fine to do it this way. So those colors are the different rays. I mean, the different intensities for each ray, heliocentric angle, sorry. And then we have squares and solid. So solid is the CAD computation, the first one we did. And then squares corresponds to PRD. Okay, so then what we are seeing here is that colors to the red are larger heliocentric angles, and colors to the blue are close to the limb, so lower heliocentric angle. Okay, and then here I added as an offset the difference between CRD and PRD for each heliocentric angle. Okay, so then you can see that in the wings they are basically the same in all the cases, and then there are some difference in the line core, and you can say that they are basically the same. They are not so big and they are not so different between almost this center and close, very close to the limb. Okay, but there are some difference. Okay, so now let's see what happens if we go to one of the blue lines. So for example, calcium H. So now here things are much more different, right? So again, these are colors correspond to a specific heliocentric angle. So we have close to the center, close to the limb, and then squares and solid are PRD or CRD. So if you see the difference now, it's really clear that close to this center, the differences are relatively small, but for lines that are very sensitive to PRD, as soon as you move to the limb, then you can start seeing larger and larger differences. So in this case, close to the limb or at 0.25, the differences are very large. So in other words, I would use this type of plot or this type of study to verify if the line of interest, the line that you want to study, it's really sensitive to PRD or not. So you can compare just, I don't know if it will be easy to see it in the screen, but I will just try to put one close to the other. So you can see that the blue line and the red line are basically the same, while here blue line is very large. Red was already large, but blue is larger. So you can say that in general, probably 8542, it's not really sensitive to PRD, or at least not at the level of calcium H and K. Okay. So,
oh, Carlos,
yes.
I have a question, maybe
yes.
for Hannah. I don't know. Can you tell me why going towards the limb, the PRD effects become so much more important?
Yes, maybe Han. I think it's geometry, but maybe you can add more.
Yeah, it has to do with really the source function in the case of CRD being wavelength independent, and so you sample it higher, while in the wings of the PRD source function falls off from the Planck function more, so it doesn't show as much of the emission peaks. So it is geometry and the behavior of the source function that is different.
Okay. Right. Well, look into that.
Okay.
Well, yeah, you really have to look at the source function plots to it's not easy to understand just hand waving here.
Yes. But essentially, we can say, Han, that as soon as you move from this center, you would expect larger impact from PRD.
Yes.
This, yeah. Okay. So, any additional questions?
I have a doubt here. So maybe it is like very naive. So as you show that in the spectrum and geometry itself, we can have these line profiles and see. So what is the extra level of calculations which Solvray is adding when we generally do the computations.
So you mean, oh, I think I couldn't follow. So you ask,
Okay.
How is the impact of using solve ray after using this?
Yes, yes.
Oh, maybe if I understand. So are you asking if we can use directly the red line instead of asking for solve ray to compute exactly mu equal 1?
Yes.
Okay. Yeah, it's a good question. I think solve ray is really fast. So this is 0.96. So it's not exactly 1. So I think the time required for doing solve ray, it's probably worth it because it's really fast.
Okay.
What is, yes, I think what is really taking time is the non-LT problem, but solve ray, it's just converting all the things that RH has already computed. So I think it's really fast in terms of the time you need compared to the non-LT problem.
So it mainly adds like more precision to what mu we are looking at.
Yeah.
So typically it is really meant to calculate the intensity at the exact heliocentric angle that your observations are. So in general, we set solve ray, the ray dot input to be the vertical direction because that is typically what you look at. But in general, you can calculate exactly the energy, the intensities at the heliocentric angle that your observations are for a better comparison.
Yes.
Okay. Now, if you use only 3 n rays equal 3 or so, then your the closest to this center is only 0.89. So it's still.
Okay.
Yes.
So then you cannot really do this. If you just don't want to use solve ray and be close to this center, have your most vertical ray close to this center, then you can just increase your n rays and do that as well.
Yes.
But this is to find the balance between not doing too much in calculating all these rays and having the accurate intensity at the heliocentric angle that you wish to have.
Yes, two things.
Okay.
So my impression, and I don't have the numbers here, but for example, solving 5 rays and then using solve ray is usually faster than solving, for example, 7 rays with one falling in the wavelength that in the heliocentric angle that you are interested on. And also, for example, in this case, we, as Han was saying, by default, we use 1, but imagine that your observation is at 0.85. So then with 5 rays, you are either 0.75 or close to 1. So then 0.85 is in the middle. So then in that case, it's much better to use these 5 rays and then solve ray, but just specifying 0.86, for example.
Yeah, okay.
So to clarify, the reason that you cannot select arbitrary angles in the non-LTE calculation is that you have to have an accurate estimate of your radiative rates, and the radiative rate is determined by integrating the radiation field over all wavelengths across the line and all angles. And to have the most accurate representation of the angle grid, you use basically the 0 points of the Gauss-Legendre polynomials. And so that dictates the exact values of the mu's that Carlos is showing here. And so it has to do with getting a best estimate for the radiative rates in the non-LTE problem that you have these angles. And then if you want to compare with a specific angle, you have solve ray, which basically takes the population numbers and the angle average mean intensity and does a formal solution for those values in exactly the direction that you wish.
Yes, and it's usually faster because there's no iteration involved. So it's just taking what you have done and then just solving for a specific ray. So yeah, I would say that if you are around 5 rays or even a bit more, probably it's still faster to just solve RH non-LTE problem and then just pick with solved ray, the one you are interested on. If you are lower than 5, then definitely you need to do it, because it's probably not going to fall on the close to the region you are interested on. Okay.
Yeah. Okay. Yeah.
Okay.
Thanks.
Okay. But your question, Nancy, is good, because in the case of angle dependent, as we said before, solved ray will not work. So if you are solving PRD with angle dependent, then in that case you may play with the rays, then reading this geometry structure, and play with the number of rays, 5, 6, 7, until you have one ray that is very close to the heliocentric angle that you are interested on. And then in that case, you solve with angle dependent, and then you pick that ray as your solution, and you don't run solve ray for that case.
Yeah. Okay.
Okay. Okay. So then yes. So I was saying that we had a strong difference between calcium H and very small difference for calcium infrared. And I think this is almost the end. You have the plots. If you have any questions, just let me know. But basically, I'm just I'm normalizing them to some continuum that I put it here, and I'm just putting one with both with the same color for a given heliocentric angle, and then adding just a square in one case and solid line, and then I'm just plotting the difference with an offset. But if you want to repeat the plot and for any reason you don't understand something that I did, just let me know. Okay, so then what I was saying, I believe that in general, we can assume that non-LT and CFD is enough for the infrared lines. But the calcium 2 H and K transitions, they definitely require PFD, okay, for properly solving them. And as advice from what Hans said, it's probably also good to have PFD switch on for the calcium infrared. So I mean, maybe, and I think we can go back to this when we are doing the design tutorials. Maybe the best configuration is something like this. For if you imagine that you have the decreased upcoming data with calcium 8542 observations, polarimetry with VISP, maybe the best way is to put void CFD for the infrared lines, but keep PFD for the calcium H and K. Okay, this is what Hans said at the beginning, and maybe we should do it. So when we go to this part in this side, we will try to do it this way and check that it's working and it's better. Okay, there's an extra comment because when you run this test, you may see that, just let me go back. So in this case, so when I run the test, we had this configuration, okay? So we have this hydrogen atom, okay? And when I solved the calcium K line, I saw this part and then this transition here. As I'm used to use RH, I knew that this is a satellite transition that comes from a given atom that is included in the atoms.input file. So what I want to say is that sometimes when you have a transition on these passive atoms that falls on the wavelength region that you are solving actively, so in this case for the calcium atom, you can see these satellite transitions and they come from the other atoms. But as you can see, it's not properly solved because in this case, it comes from the hydrogen atom. So it's not properly solved because the atom is in passive mode. So then you have two options there. And the two options that you have is, yes, first one is to change the atom. So the computations that you saw today are computed like this. So this atom has less levels and also less transitions. So then this transition is not present. Or the other option is to keep the atom, but then put it as an active. Okay. So if you do this, then this line, this satellite line that's here, it will be solved with high accuracy. Okay, so but just this is a extra comment that I saw, and I believed that probably you will find it as well. So if you see something weird, like an extra line that should not be there, it's probably coming for either the Kurux line list, that in this case we don't have, and we will see in the future, or from some transition that is included in your passive atoms. Okay.
This is H epsilon, by the way,
yes.
Balmer epsilon.
Yes, yes. So then this transition that Han mentioned is included in this atom, but in this simplified atom is not included. So if you do the computation like this with passive, you will have the clean profile that I show you today. If you do it like this, you will see that transition over there. Okay. So it's just a comment that I found it, and I said it's worth it to show you, and then just keep it in mind that these things can happen.
Carlos.
Okay. Yeah.
I have a question. Why do you have in this atoms.input file the sodium and potassium as zero radiation?
I think it's fine if they are passive. I think they, well, maybe Han can correct me, but I think it doesn't matter.
No, I'm talking about the initial solution.
Well, if they're passive, they regardless of what initial solution says, they will take either the values that are read in via the population file from a previous calculation, or it will be assumed to be LTE.
No, yeah, I know, I understand that, I know that, but why? I mean, why don't you change it? Why don't you put LTE populations instead of zero radiation? I mean, there is a physical meaning for that, I guess.
Only if you solve the sodium or potassium as active.
Okay.
Yes.
So
yes.
Okay, so that's okay. Okay.
Yes. The idea is that this is a reference file. So then maybe some time ago I was doing computation of sodium and I had it like this. Okay.
I got it.
But
okay,
then I put it in passive. And in this case, as I think I explained it, but if not, I can say it now. I usually remove everything after computing. So then in this case, it will be always LTE. So the code will not have any file from where they can start with. So it will be LTE. And in this case, even if I'm saying zero, it will use LTE.
Yeah.
Okay.
Yeah.
Okay.
And if you were to use the populations file, you would have to say all populations actually.
Okay, thank you.
Yeah. But Alberto, is a good question. So the next question is, if I put it as an active, which value should I put there? Zero radiation or LTE? We said last week that for cases where you have strong resonant lines like magnesium 2 or maybe calcium 2, it's probably better zero radiation. In the case of sodium or potassium, the truth is that I don't know. In fact, I don't remember if I put it this way. So it's,
I think either works fine.
Yes, I think you will not see big differences in any of the cases.
Okay.
Yeah.
Thank you.
Yes. Okay. So then we were, in this part. Okay. Yes. So then the summary. And I hope you will have questions after that, but just let me try to bring the general concept of this class and the 3 classes that in fact we had on this topic. So first, PRD effects are essential for certain lines. And these are, in fact, one of the most interesting lines on solar physics. So they are the magnesium 2 H and K, the calcium 2 H and K, and also the Lyman lines. I put alpha and beta because are one of the strongest from the Lyman series, but in general, all the Lyman lines, I think they need to be treated in PRD. So then we need to solve them with PRD if we want to synthesize them properly and compute the populations of the levels where they are, where those transitions come from. But at the same time, as you saw today, lines like the calcium infrared 8542, it seems that there's no big difference between PRD and CRD. And it's really a big difference in computation for that line, and also how you treat the polarization. So then I would say that it's safe to assume that they can be treated on CRD, and we can do it in the future. So, and some examples of things that we can do with high accuracy right now. And this means, for example, inversions with either DSI or stick, is that you can switch on like we have now. So in this case, PRD for calcium HNK and CRD for calcium infrared. So imagine that you are at SSD. You have observed with chromis, that is intensity, calcium either HNK. So then in that case, you will solve the two HNK transitions with PRD. But then you also have polarimetry in 8542 with CRISP. So then that transition, you solve it with CRD, but with polarimetry. So you can do both things. Another example could be, imagine that you have an iris observation of magnesium HNK. Those transitions need to be treated in PRD, but it's only intensity. So you have the highest accuracy that we can achieve. But then you have a coordinated observation with, I don't know, SST, CRISP, or IVs, or the keys in the future with the VISP. So then you have polarimetry here. So again, you set CRD, you do polarimetry, and then you set PRD with those magnesium HNK lines. And this should work in the future with either stick or DSI. Okay. And then why I'm saying this? Because at least in DSI, the same things that we did today, so configuring this calcium atom and configuring the keyword.input, you will have to do it. So then it means that everything that we have learned today and in the two previous classes, so the number of iterations or how to check the nullity problem is working properly, where you want to set PRD, how many wavelength points you want to add, should you add asymmetric or symmetric. So all those things are going to be the seed of DSI and stick. And in the case of DSI, we will use the populations and also the profile from RH for starting all the inversions that we do later. So then it's really important that you have a good configuration for RH, because otherwise the seed that you are going to use for the inversions could be wrong, and then the inversions will not improve from there. So then these three classes that we may think that we didn't move very fast are critical for all the input that you will need for DSI and I believe also stick. Okay, so try to revise them, try to grasp or understand everything that we have said, because it's the basis for future inversions with codes based on RH. And it's the same file. We don't change anything. Okay, so everything that you do today, you can just copy later on the DSI folder. Okay, so, and then just comments, you can experiment with polarimetry and PRD, angle average, the one we use today. You may try to use a strong field where a Zeeman effect, where the Zeeman effect is the dominant. So you may try to see if this works. But we don't know exactly how valid it is. So just take it with, I don't know if grain of salt is the best way of saying it, but just be careful. And also experiment, as always, with the NG acceleration. Today was working fine without NG acceleration. So we can leave it like that. But if you see that systematically is faster and stable, so then you can switch it on. But it's something that is basically problem dependent, or at least atom and atmosphere dependent. So it's not clear to give you a recipe for that. Okay, so then before moving to the presentation, is there any specific question of what we saw in the script or the plots or something here related to the atom or the keyword.input?
Carlos,
yes.
So for Balmer lines like H alpha and H beta, PRD is not important, right? It's negligible effect, and we are not using PRD for those lines.
Yes. Yes.
Yes, correct. Yes.
Yes.
Okay.
Yes. Yes. And my advice, if you have time, try to do what we did today with H alpha. So you go to the hydrogen 6 atom. We can go here. So if you go to the RH distribution, you go to atoms, and you have, for example, this one. So here you have the Lyman lines and then the Balmer lines. If I'm correct, I think this is H alpha.
Yes.
So then try to play. So just run one computation with void and one computation with PRD, and try to read the 5 angles and overplot like I did it. And you will see that is again, as calcium infrared, is very, very small difference. But if you do the same with this one, that is Lyman alpha, you will see that the difference is really, really large between CRD and PRD. And at the center, definitely, but also at the limb, you will see that it's even larger. So these lines are sensitive to PRD, and this one, we can assume that they behave well with CRD.
Yeah. And the reason is that the H alpha line source function is already very much a scattering source function. So you add PRD, it's not going to change the source function in the wings because they're already like they would be in the wings.
Yes. Yes.
Even if you are at the extremely low heliocentric angle. I mean, even for limb observation, limb geometry.
That I wouldn't be 100% sure. I don't think there's big differences, but it's something you can definitely try.
Yes.
But then I would think that in general, geometrical effects are much more important, and that PRD is a little bit different, but maybe not important. But it's certainly trying. I don't remember. I don't remember if I've done. I'm sure I've calculated it, but I don't remember what towards the limb. I would be surprised if it makes a difference or significant.
Yes. 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 That I think in this case will be just switching. So in the atoms of input, you put like this. You put it as an active.
Yes.
And then you just run twice. One with PRD here and one with CRD, and then just copy the plots I made here. You need to change the wavelength because the lines are different, but the concept will be the same. So you will have 5 rays, and you just plot one on top of the other, and then you plot the difference between one ray computed in PRD and the other ray computed in CRD. And then you can check what happens when you go to 0. That is close to the limb.
Okay.
Yeah.
Thank you.
So in the case of the sodium D lines, there PRD becomes important,
yes.
and the situation of the source function is very similar. So I would expect it maybe to be similar in H alpha. Is that at heliocentric angle smaller than 0.1, you start to see differences between CRD and PRD.
Okay. Okay, thank you. Okay, any additional questions?
I have a question.
Yeah.
So for the calcium to H and K lines, how important is the cross redistribution? Will the profiles be very different if I just do it with PRD as compared to XRD?
Well, Han, do you want? Or
so the calcium H and K won't change much because they are such strong lines. They basically determine themselves. Now the infrared triplet lines share upper levels with the H and K lines. So what is more likely a scenario is that there will be an excitation in H and K, and then a spontaneous emission in one of the triplet lines. And in that case, you have to take into account the correlation between the exciting and the de-exciting photon. And so for the cross redistribution is more important for the infrared triplet lines than it is for the H and K lines.
Okay.
But under normal solar circumstances, the difference between regular PRD and cross redistribution in the infrared triplet lines is not very big. There are lines for which it is very important, and those are the oxygen 1 lines at 130 nanometers. For those, you really need to calculate cross redistribution, because all those 3 lines, the 3 oxygen lines, all share the same upper level. And there, if you neglect cross redistribution, you're off. But that's basically the only example that I really know where it really matters.
Yeah, thank you.
Okay. Yeah. But as an exercise, you can also try to just switch on PRD for the calcium line and then overplot the result of using like this, or just putting XRD true here. And then at least for one ray or for one heliocentric angle, you may check if it's very different or not. But I think it may be more accurate, but I don't know how different it can be. Okay.
Yeah, I have a follow-up question.
Yes.
How important scattering is in the case of magnesium HNK pair?
You mean how important is considering PRD or?
PRD definitely,
Yes.
cross redistribution, and also in case if we can include scattering physics in the problem.
You mean for polarimetry?
Yeah. And also in the intensity case, in case if we want to fit magnesium HNK in the case of iris. So how important it is?
Well, yes, in magnesium HNK, since magnesium abundance is about 10 times higher than calcium, the magnesium HNK form higher, where scattering is more important. So PRD is even more important than in calcium HNK. Now, the situation with the triplet lines is slightly different. The triplet lines, actually, the levels, the D levels, which are the lower levels of the calcium infrared triplet line, lie below in energy, below the P levels, which are the upper levels of the HNK and the upper levels of the 8542. So the triplet levels are not as important. So in magnesium HNK, since the HNK lines have different upper levels, cross redistribution is not important. So you can ignore cross redistribution in that case. But you do have to use PRD.
Yes.
Okay.
So then in this case, you would recommend to switch PRD, for example, like this case with 10 iteration with a reasonable number. And then this one, in principle, we can leave it like it is for magnesium HNK.
Yes, correct.
Okay, but for intensity. So I think, because just let me confirm, Han. So we are not including a scattering in polarization. We're just including
scattering polarization in the line. No,
yes,
we're not including that.
Yes. So we cannot model.
Don't have atomic polarization.
Yes. So it will be definitely important, but we cannot do it in RH. So I think this is one of the answers. So we can include the scattering that you saw and the cross redistribution only for intensity, but when modeling the polarization, we are including the Zeeman effect only.
Okay, thank you.
Yes. Okay. Yes. So then, any additional question? Okay.
I have, Carlos.
Yes, Albert.
I have a comment what is very related with the comment you made about taking into account very carefully what we put in the keyword input. file for the inversions.
Yeah.
So what you have done today, it has been very, very clear, and I really like it. But there is something that I'm missing, is that you are comparing, you have shown how is the difference of considering PRD or CRD in these lines.
Mm-hmm.
And you can see that there is a difference. In some lines, this difference is obvious.
Yes.
But that's the only thing you can see. You cannot see how is that related with the sun. So you see there is a difference between the PRD profile and the CRD profile, but you don't know how it's compared to the sun. So I think that it could be beneficial to overplot all the time how is the average profile in the observations for these lines in the whatever mu you won't consider. Because otherwise you are just telling there is a difference, but what is that telling us?
I understand, but if you give me the model of the sun, then
no, it's not well, you go to your observations to the quiet sun, or
yeah, but
and you can have some approximation. Here, the only thing I've seen is that some lines, they have a difference between PRD and CRD, but that is not telling me anything related with the sun. And this is exactly what you said in your comment about the inversion, is that you have to have a combination of these PRD, CRD combinations with respect to the sun.
Yeah, I mean, I can see your point, Alberto, but the PRD is just a more complete physical picture. So
no,
PRD is
I
always more accurate.
No, I understand that.
As it turns out, it's also closer to what is observed, fortunately. Yeah. But it would be I think beneficial indeed to show that if you would use CRD, you would be wrong. You cannot reproduce solar profiles.
Yeah, I just want to point that yeah. Yes, you are.
And for this center magnesium or this center calcium HNK, it's not that clear. By the way, it's only in calcium HNK. It's only very clear and obvious when you go towards the limb. There you really see that CRD is a completely wrong approximation. For magnesium HNK, it is immediately clear at this center.
Yeah.
Yes. I think so. I understand your comment, Alberto, but today, and also the previous day, I will just focus in on adding physics that we believe that are correctly defined, and then check if the line is sensitive to this new physics. So for example, in the calcium infrared, adding PRD or not, basically it doesn't change the line. So then it means that you can survive with that. The problem is that if you want to have an atlas of calcium 2 at different heliocentric angles, like I did today, I'm not sure if I have that. So like 5 rays at 5 different heliocentric angles for calcium HNK, I'm not sure if I can do that. And most important, I don't know if the atmosphere I'm using is the one.
Think, as I said at the beginning, I think you made a great job. I think it's very clear that your statement that there is this difference in considering this physics. But again, I think most of that things here are solar physicists, and we should keep in mind that what we are trying to understand is the sun, and understanding the physics of, in this case, of the atoms and the lines. But I mean, I have seen this plot several places and say, well, yes, but how is the sun? How is the profile in the sun? Why there are peaks here, there is wider here, but that is, how is that related with the sun? It's a little bit related with the comment you made in considering this for the inversions, right? If you don't set up well these things, your profile is never gonna try to match or be able to match the sun. So I agree with your point, but I think it would be beneficial to have some reference, like, oh, look at the profiles in the sun, looks a little bit like this, and you are missing these winds or whatever. That's cool.
Yeah. Okay. Yeah. I think I will try it, but just as a comment is that maybe, well, at least with this side, if you don't embed with PRD, you may match the observation. But the problem is that the atmosphere that you are getting is probably wrong. So what we are assuming here is that first try to define the better physics or the best physics that you can have. And then we will match the profile with a probably better atmosphere than the one that we could get.
Yeah, that's totally right. That's totally right. As said Hans, for example, for magnesium is not possible. You see clearly that you need a PRD. You cannot have the situation. But yeah, it's a convergence between the knowledge of the physics and what we observe. So yeah, that's that.
Yes. Okay, but thank you for the comment. I will try to make it like that if possible. I will try in the next class.
Yeah, there's Atlas for point 2 as well.
Yes, the solar.
But you're right.
Second.
It's difficult to find general profiles for all our usage.
Yeah.
Maybe Dicky should do one of these atlas.
Yeah, I mean, it's true.
Yeah.
I don't think that Dicky, I think that should be done at the DST or something.
Yeah.
Because you don't need resolution for it.
Sorry. Okay, so this one. So then, any additional questions? No? Okay. So then, as a homework, as always, try to run the test I prepared. One exercise, we have said today that there are several exercises, but one could be try to do exactly the same, but for the other two infrared lines. So 8498 and 8665, I think is the two infrared transitions, just to check if you see the same behavior, that PRD seems to be not very important for those lines. Then I already included these. So sodium lines are also additional lines that you probably see that PRD it's important as you move to the limb. So maybe you can try to do it. Just switch to active the sodium line. Look for the sodium transitions that I think are the first ones. I think it's from 01 and 02. And then just try to see if you can do the computation I did today for this atom and check if PRD seems to be important for those lines. As I said before, try to understand everything that we have done, because it's going to be the initial configuration that you will use for design. So you will set nodes like we did with SER. You will set different inversion configuration. So temperature will be a free parameter, magnetic field, velocity, but we need to solve a non-empty problem. It will be done by RH, and it will be done with the same files that we use today. Same keyword.input and same atoms.input. And for example, in the calcium atom, the same calcium atom file. So PRD void will mean the same, and QCore, QWin, and lambda, everything will mean the same. So try to understand it, because you will use it later for any transition that you want to solve in non-empty. Okay. So then next class, we will continue with RH. I think, I'm not so sure, but I think we will focus first on adding Lte lines. In this case, we will have the calcium infrared 8542, and we will add satellite lines that are in the wings, and you will see how this is added to RH. And then you will see that this profile is getting closer to the Atlas. And then, yeah, you will learn how to do it. It will be in a few weeks, because I'm going to take holidays. So the next class will be in late August, on Friday 27th. I will send a reminder probably at the beginning of the week and then the day before. And I will enjoy the holidays, but I probably also prepare some part of the class, because it's always good to be advanced. But I think that I would like to also wish you nice summer holidays for those that have not had it yet or will have it. So enjoy the holidays, and just ask any question that you could have before I close? Okay, so then I stop sharing. Again, thanks everyone for being here today, for the questions and for the participation. I think this is important for making this more interactive and helpful. So thanks a lot. And I hope to see you in almost 1 month. Okay.
Thank you, Carlos.
Okay, bye.
Enjoy summer.
Thank you. Bye.
Thank you.
Bye.
Thank you, Carlos. Bye.
Bye.
Bye.